Hello, everyone. Welcome to our live stream for Monday, May 8th. We are happy to be here. It's approaching the end of the semester for us, but our online classes go forever. And so we know that you are around the world and joining us in various days and times, and we appreciate you being here. Um, my name is Matthew. I'm one of the instructors for our online classes, and I sort of run things behind the scenes here. Um, I'm going to let Professor Impey, I'll let you, Chris, say hello to everyone. We'll go over the sort of organization for how people ask questions, and then we'll get started.
Okay, welcome everyone to the online sessions or sessions for our online classes, which if they don't run forever, at least until the sun becomes a red giant, so quite a long time. The floor will be open for any question in astronomy.
Excellent. Thank you very much, Chris. The very first question that we have is from an email. And we always get great physics questions from Wendy Traver, who sent an email today. Is it possible to construct a space telescope that can see at multiple wavelengths simultaneously? Why or why not?
Yes, you can have panchromatic instruments and on the ground and in space. Space is better because, as Wendy understands in the question, the wavelengths that are absorbed by the Earth's atmosphere in the infrared and ultraviolet travel through space freely. The problem is you need different kinds of detectors. So there's no single solid-state detector that can detect an enormous range of wavelengths. But there are detectors that can detect a factor of 6 or 7 range in wavelengths, so it extends from optical into the near-infrared or from the near-infrared to the mid-infrared. Once you get to short wavelengths, you tend to need different types of detectors. So the limitation in instrumentation is really at the detector end. You can certainly have optics that work for a very wide range of wavelengths, and that routinely happens in instruments. Also, as there are issues, of course, are that the diffraction limit and the image quality vary with wavelength. Just the Rayleigh criterion is proportional to wavelength. So you don't form images of the same quality at different wavelengths, even if you do use one instrument to detect them all.
Excellent. Thank you very much. The next question is from one of our live participants. A supreme scientist asks, are there any areas of overlap between astronomy and astrology? And if so, how can we distinguish between scientific and non-scientific claims in these areas?
Well, astronomy and astrology share a long joint history. So not just overlap, but they were under the same umbrella for hundreds of years, actually thousands of years. Astrology as a formal practice goes back thousands of years, was certainly practiced extensively in Roman times, and then ever since. Formal astronomy, of course, goes back thousands of years too. And so it's a pre-scientific idea that the positions of the planets or the stars, or at the time of your birth or from month to month, affect behavior or personality or all the various ideas within astrology. That's a pre-scientific belief. It has no basis in fact, and there is no evidence to support it. So there's a clear demarcation for all scientists between astronomy and astrology. Astronomy is a scientific practice and astrology is not. But in the cultures of pre-scientific era, before the times of Newton and Galileo, say, that line was blurry. And it's well known that some of the Renaissance astronomers like Kepler and Brahe cast horoscopes. So they acted as astrologers even while they were doing astronomy. So the demarcation was blurry then. Now it's sharper, or at least should be sharper, because there's no evidence that astrology is a science.
The next question is from one of our live participants. Let me get to our questions. Dion Mac asks, what role, if any, does philosophy play in astronomy and astrophysics?
Well, philosophy is an important backdrop to all of the sciences, not just astronomy and physics in particular. Because philosophy asks some more profound questions about how we know something, sort of epistemology, the subject of knowledge. How do we know something to be true? It also asks deep questions about the nature of reality, and sometimes these go beyond things we can do in a scientific experiment for. Philosophy also addresses questions of value, and science is not usually involved in determining value or judging value of something. So, but there's a use for philosophy in astronomy, and some of the uses are for asking thought questions, provocative questions, counterfactual questions, things that might be but aren't. These are interesting ways to address the nature of reality and the universe around us.
Excellent. The next question is from Maxwell Bennett. As a layperson, how can I stay up to date with the latest developments and trends in astronomy?
Well, and astronomy moves very fast. There's a very large literature. So there's a whole range of ways you can stay up to date. At the level of nice articles on astronomy topics, you can do the monthly magazines, Sky and Telescope and Astronomy magazine. Sky and Telescope is a little more steered towards the amateur astronomer. So a lot more stuff on technical stuff and optics and how to choose a telescope. Astronomy magazine has nice features on various astronomical topics, and they go to some depth. So that's a single good source. You can also go to a website called Science News, which is takes the publicity feeds of all the major research institutes, and it publishes nice short abstracts and summaries of scientific discoveries, and you can just filter on the keywords. I think you can do astronomy and you can do space, and then you could have a feed like an RSS feed and get that weekly. If you really want to get technical and do a deep dive, you can go to what astronomers call the archive. That's arxiv.org. And that's where research preprints go in astronomy, and that's the research literature before it appears in a publication. And you can read the abstracts. They're sometimes, maybe often written at a level you can understand them, and then the PDFs of the articles themselves, which are obviously technical. So there are different levels at which you can keep up with astronomy.
The next question is from DS, who asks, do you think that AI, artificial intelligence, will be a major part of astronomy in the future? And if so, how?
Yes, AI is already a major part of astronomy and will continue to be in the future. I've just written an article for the online magazine called The Conversation about AI and astronomy. It just came out a few days ago. So AI is a part of astronomy because astronomy deals with large data sets. And also astronomy deals with digging signals out of noise. So when you take a deep picture of the sky, most of the pixels are just dark sky or noise, and then there are faint galaxies scattered around the image. And humans are not perfect at picking out the faint galaxies, either counting them or going to the limit of the data or describing those faint galaxies. And so AI has been used for a couple of decades, not just in the recent surge of AI use around different fields, to help detect things in faint images, to classify galaxies, to search for moving objects, to detect exoplanets in Kepler data. There's a whole range of ways that AI is being used. And it's in two basic flavors. Sometimes AI is being used just to search for the needle in the haystack, to search for rare or difficult to detect events. And then another very interesting way AI is being used is it's being used to take theoretical ideas or expectations and work them into a prediction of what you would see in data and then search for that. And that's a way of using AI to make discoveries in astronomy, a phenomena that we didn't know about. And that's a very exciting use that's increasing.
Chief Senior, who's on with us live, I'd like to know, what are some of the ethical and philosophical considerations that would arise if we were to make contact with an extraterrestrial civilization?
Yes, there are enormous issues that will arise if we ever made contact with intelligent extraterrestrials. The ethical issues, of course, involve the nature of the communication, the nature of the contact. Who was doing the messaging? Was it message from them that we received, so they were intentionally communicating? Or was it a message that we sent that was somehow received and responded to? So it depends on who's originating the communication. It also depends on the intention behind the communication. Was the communication, however it was received, just out of pure curiosity, or was there some intention? And it could be a malign intention. It might be for checking out for conquest, and that would be a bad situation ethically and philosophically. Or it may be that the civilization is benign and wants to share their potentially superior knowledge with us. The ethical issues come to the fore because there's no international body that's really organized to decide how we communicate. Astronomers self-organize, and they have groups and committees to try and address these issues or think about these issues, but there's no world governing body like the UN that's actively considering how to respond if we received a communication. So I'd say there are huge ethical issues that are simply not addressed at the moment.
The next question is from Meet Gilani, who asks, can you explain the current advances that are being carried out in inflationary cosmology?
So inflationary cosmology has been around for over 4 decades. The first papers on inflationary cosmology were 1980 and 81 by Alan Guth at MIT and Andrei Starobinsky, a Russian theorist, and a couple of others in the same year. And since then, the theory has evolved somewhat, and it's been tested at some level. Basic inflation has passed several of the tests that have been used using microwave background radiation measurements of the Planck satellite, and it's passed those tests. The theory hasn't evolved that much. There's still the idea of basic inflation, the exponential unfolding of the universe from subatomic scales to macroscopic scales, and then slowing down to a conventional Hubble expansion. There's the idea of internal inflation, where the quantum origination of the universe was just one space-time event, and there may have been other space-time events either in parallel or in the past in a long time sequence. And chaotic inflation, which is another variation of the basic theory. So there haven't actually been any fundamental advances in inflation theory. There's a lot of papers written about it theoretically, but at the moment it's really waiting for more experimental tests to show that the basic idea is valid.
That's kind of a nice segue into Jake Johnson's question, which is, can we reconcile the apparent conflict between observations of the accelerating expansion of the universe and our current understanding of gravity, or do we need to modify our theories of gravity to explain this phenomenon?
It's not clear how we relate the accelerating expansion of the universe to gravity theory, because the accelerating expansion of the universe is, of course, something that implies negative pressure. It actually is going against gravity, so it's in opposition to gravity, which will tend to slow things down in terms of expansion. So it's really not in the same ballpark as gravity, and it's a very different entity, we think. So therefore, it's not assumed that dark energy, the existence of dark energy, is going to require any change to gravity theory. There are other reasons why we may need to move on from general relativity. Dark energy is probably a property of space-time itself, and so it's going to require a sort of fundamental physics advance to really understand it. It may have some connection in the end to gravity, but it's not clear that it needs to.
Thank you very much. The next question is from Kendra Smith. Do variations in the solar output, such as changes in the amount of energy emitted by the sun over time, impact the climate of Earth and other planets in the solar system?
Variation in the sun's output do affect Earth's climate and weather, but not in a way that is often claimed by people who are denying that climate change is happening. There's an argument out there in a small minority of people, it's basically disinformation, that climate change that we are witnessing worldwide is caused by changes in the sun's energy output, and that is simply not true. The sun does have varying solar output by a very small amount, less than 0.1%, and it does follow a solar cycle, 22-year cycle. But that doesn't correlate with climatic events that we're witnessing. So the effects on the Earth climate are subtle. The strongest effects on the Earth climate are associated with the rise and fall of geomagnetic activity in the sunspot cycle, because that geomagnetic activity sends high energy particles and cosmic rays towards the Earth, and that interferes with our magnetosphere and affects global telecommunication. So those are the most profound impacts we see on a cycle of 22 years. But we don't see anything about the sun's behavior, which is mostly rock steady in its luminosity, that would connect to the climate change we see all around us.
The next question is from an email. Ravi Narasaman asks, there are several pieces of evidence for the existence of black holes. X-ray emissions, orbits of stars, event horizon telescope images, gravitational lensing, etc. Which one of these do you find to be the most compelling?
I would say the images of the event horizons of the black holes in our galactic center in M87 are pretty compelling because these are on the scale of the event horizon, you know, the black hole scale essentially. And when you run models of how the illumination around the black hole, I guess around the black hole should look, they match general relativity, which predicts black holes. So that's pretty compelling evidence. But in the same vein, I would add a second type of evidence that is just as compelling, that's also quite recent, which is gravitational waves. The discovery by LIGO of merging black hole space-time ripples in 2016 is definitively points to the existence of black holes, because those gravitational wave signatures, very characteristic and very particular signatures of gravitational waves, can only be fit by a model where two black holes merge. This is a very specific model, and that in the end is very strong evidence of the existence of black holes and the fact that some of them are in binary pairs that do merge.
LZL, who's on with us live, asks, how might our understanding of gravity change in the future? And what are some of the key areas of research in this field that are likely to be important in the coming years?
Gravity theory does have significant effort. It is known that general relativity is not the final theory of gravity. We know that in a number of ways. First of all, because we know that gravity theory is not reconciled with the subatomic forces described by quantum theory. Those two theories have never been merged or integrated. And so a superior theory of gravity would accommodate the existence of quantum phenomena. And there are some, lesser reasons we know general relativity is not the final story, such as the prediction of singularities inside black holes, which is an unphysical situation. So there is great research on gravity theory. Some of these are more minor variations of general relativity using the same conceptual framework, and others are real reimaginations of gravity, so-called scalar gravity theories, where you actually have a sort of different mathematical basis for the theory of gravity. It's very difficult work. There's only maybe 100 theorists around the world who are doing it. It's challenging because whatever alternative gravity theory you come up with has to be able to explain all the things that general relativity does, and it does a very good job, and then go on to explain more things and account for anomalies and make predictions that can be tested. So that's a very high bar, and that means progress in gravity theory is actually quite slow.
The next question is from Rasta, who's on with us live. How can we address issues of diversity and inclusion in astronomy research, and what are some of the most effective strategies for promoting diversity and equity in the field?
So astronomy is not the best, nor is it the worst in terms of equity, inclusion, and diversity. It is better in terms of diversity, in terms of gender and racial minorities and ethnic minorities. It's better than physics, but it's not as good, for instance, as biology. So it's somewhere in the mix. In terms of how we can do better, astronomy, tries to do better at the professional level. The professional organization, the American Astronomical Society, promotes women, has created new prizes for career awards for women and young scientist awards for women. The AAS, as it's called, has had a significant number of presidents and senior officers who are women going back decades, and actually the incoming president of the AAS is Darren Norman, who's a black woman, someone whose thesis committee I was on at the University of Washington, and that's a first. So these are small steps. That's not solving the issue completely. There are some structural things people do, trying to make peer review blind. It can be blind to racial definition. It could also be blind to gender as a way of overcoming certain types of implicit bias. And that also can be done with certain parts of the hiring process. So there are attempts to do that, to sort of make research more blind to who people are and only look at the work they do and the ideas they have. And I'd say progress there is steady but fairly slow.
Hernan Reyes sent an email Can you talk about the current or recent inquest into UFOs by NASA, led by David Spergel? Can you talk about what that's all about? Why a full-fledged inquest, and why is there this sudden interest in UFO sightings that have supposedly increased in the past 20 or so years?
So the inquest that's being referred to is a very high level body, a scientific advisory body to NASA, composed entirely of professional astronomers, astrophysicists, that's trying to look at especially the spate of UFO sightings from the military that have now been released. I think the total number over 15 years or so is about over 600. So it's a large number. And it's led by David Spergel, who is a very senior astrophysicist. He's a fellow of the National Academy of Sciences. He's former chair of the astronomy department at Princeton University, very well respected astronomer, and the committee is full of high-level people. It's a very august committee, and the question of why are they looking at UFOs, or as the military has rebranded them, UAPs, unidentified aerial phenomena. I mean, the reason is that the military has accumulated a number of these sightings, and they want to know what's going on. And they've released some preliminary reports, not this advisory group, but the military themselves, and the Office of the Director of National Intelligence has released a report last year. In none of the reports do they claim anywhere ever that little green men have been found, that there were any evidence in any of these reports for intelligent aliens visiting us. They are still, though, unable to explain most of the sightings, and that's really why they're investigating. They want a high-level body of scientists to scrutinize the data with a scientific eye and decide what they can conclude. And maybe many times they won't be able to conclude anything because the evidence is very transitory. These are brief sightings. They may only involve one mode of observation, either visual or radar or infrared, but rarely more than one. And they're non-repeatable because the same object does not tend to recur. So it's very hard to track down things like that. The why question of why are they doing this is, of course, these are things cited by military professionals that don't have an obvious explanation, so the military has a duty to understand them and try and understand them. The concern is not that we're being visited by aliens. The concern of the military is that some of these sightings may represent a superior or very advanced technology by America's rivals and adversaries like China and Russia. And that is a concern that's motivating a lot of this interest by the military.
That's very interesting. The next question is from a young viewer who says that they are 7 years old and want to learn about the stars. There are so many, and how does anybody keep track of so many, and how can I learn to do that too?
Well, there are a lot. I think the best thing you can do is go to a dark place. I don't know where you live, but most people unfortunately live in cities or suburbs where you don't see a dark sky. But assuming you're not in a super bright city, you will be able to see stars in the night sky. And I suggest that to learn what they are and start being familiar with the sky, you can either get a physical object called a planisphere, and that's just a perspex translucent sheet that's marked with the stars, and you just hold it up and orient it east, west, north, south, and then dial in the day and the time, and it'll show you what you're seeing overhead and label those stars. You can do that equally well, maybe easier with an app. 7-year-olds don't always have smartphones, but if you get your parents to put one of these apps, and there are a number of them, these astronomy apps on a smartphone, and are able to use it, then you can just go outside and point in the sky to whatever objects you like, and it will label them, and then another part of the app will give you the story of the star or the constellation or the planet. So that's a really good way to be familiar with the night sky. And if you do get a chance to go to a dark place, then you will see many, many more stars than you do in a suburb or city. Full dark sky will let you see, and good eyes, good young eyes, will let you see 5,000 or 6,000 stars. That's a lot.
The next question is from Sammy M. What kind of effects would a close encounter by a star cause to Earth? Besides gravitational effects, could they heat the Earth's atmosphere and surface?
So it's an interesting question because stars do move. You know, we are in a Milky Way with stars milling around. They have random motions in the nearby universe, say within 10 or 100 light years. And then they have systematic motions as we travel in a long, leisurely, quarter-billion-year orbit of the Milky Way itself. And those random motions do occasionally take stars fairly close to the sun and our solar system. And we've plotted these, we can track these and then even predict which stars are going to approach the Earth and the solar system. But space is very big compared to the size of stars and the size of solar systems. So the odds of a true collision or an impact or even a glancing encounter are actually very low. So you're not really going to expect to see a nearby star approach the solar system close enough for the radiation to rival that of the sun and therefore affect our climate. That would be very unlikely. The real effect of a nearby encounter with a star is not in terms of brightness and what happens in the sky, but really gravitational, because a nearby star having a glancing encounter with the solar system could well perturb planets in their orbits, in some cases tossing planets from their orbits and destabilizing them, and that could happen to the Earth. So that would be a very dramatic outcome if for a very close encounter. But we don't have to worry about that, particularly because people know where the nearest stars are, which direction they're moving, and can predict which ones are going to come close, and nothing is going to come dangerously close in the way I just described for tens of thousands of years.
As sort of a follow-up question, Mark, who's on with us live, would like to know if there is an effective way to accurately measure the influence of nearby stars on our planet or solar system.
Yeah, you can certainly measure the influence, and it's just a gravity calculation. There's a concept in Newtonian gravity theory called the sphere of gravitational influence, and it basically describes the distance out to which one body governs the motions of another body or other bodies. So the Earth has a sphere of gravitational influence, and the Moon is within that, and so the Moon is captive around the Earth, and although the Moon feels the Sun's gravity, it's by far dominated by the Earth's gravity, and so it's orbiting around the Earth, and then the Earth and the Moon together orbit the Sun. You can also define the sphere of gravitational influence of our whole solar system, and that's the way of thinking of the edge of the region where significant effects are felt if another solar system comes close. So you can put a number on this distance.
Mark would also like to know, how have the positions of the planets changed in the past 2,000 years, both in respect to the sun and the galaxy?
The planets in our solar system have well-determined orbits, and for millennia, or centuries and millennia, they've just been continuing in their orbits, and those orbits really don't change on those timescales. On very long timescales, eons, hundreds of thousands, millions of years, those orbits can change very slightly. But basically, the planet orbits do not change on timescales of thousands of years, so you can predict the positions of planets for hundreds or thousands of years in the future, and that's something you can do with a calculation and an app, and a planetarium does that to predict what the sky will look like in hundreds or thousands of years.
Thank you. The next question is from David McKenzie, who sent an email. Do astronomers have any idea which stars, if any, were created from the same molecular cloud as our sun?
It's an interesting question. The answer is no, and that's really because the archaeology is too hard to do. So the sun and the solar system have been around for 4.5 billion years in a galaxy that's probably 11 or 12 billion years old. And we orbit the sun, and we orbit the center of our galaxy 4 times in a billion years. So if you do the math, then the sun and the planets have been around the galaxy 18 times. And in those 18 orbits of the galactic center, the sun and the planets move up and down out of the galactic plane, encounter nearby stars, suffer perturbations or gravitational nudges from nearby stars, and all the gas that might have been around from which the sun formed, and possibly other stars, has long since dissipated or been dispersed by the rotation of the galaxy. So for something that happened that long ago, 4.5 billion years ago, in a dynamic entity like the Milky Way, there's no way to trace back and find out what were our neighbor stars that formed together, because probably there were neighboring stars, and where they are now.
Donald Spicer has a question. This is very recent news from the James Webb Space Telescope. The article that I'm seeing on it is actually from today. But I was wondering if he was wondering if you had heard about the discoveries related to Fomalhaut, the star, and if you could explain these discoveries and add any more to it. I guess these are the finding a star cloaked in three rings of ruined worlds is the title of the article.
Right. That news came out in research circles some weeks ago. So it's very interesting that you can have debris around stars. Of course, you can have failed planets. The asteroid belt in our solar system, pretty far from the sun, is a failed planet or planet that was ripped apart and the material just dissipated from that orbit over billions of years. So this Fomalhaut discovery is a more dramatic example of debris quite close to a luminous star that represents either a failed planet or a planet ripped apart by tidal forces. I don't think it's completely clear which at the moment.
The next question is from Gulam Bogans, who's on with us live. Can you explain the concept of time dilation and how it affects the perception of time and space? I'm having trouble making sense of it.
So time dilation is a basic prediction of general relativity, and it basically says that in situations of strong gravity, clocks run slower compared to clocks that are in situations of weak gravity. So if you take a clock, if you had two identical clocks keeping synchronous time, and you leave one in deep space with no nearby gravity operating, and then you take one anywhere, actually, surface of a planet or near a star or into a black hole would be the most extreme version, then that clock will seem to run slower than the one that's in deep space. So this is a measurable effect, and time dilation has been measured in the lab, actually, and it's also been measured indirectly in astronomical situations. So it's a simple relativity prediction that the stronger the gravity, the slower the clock runs. And when the gravity is strong enough to create the situation of an event horizon at the edge of a black hole, then according to the formulae, the time dilation is infinite. In other words, time stops. Time freezes at the event horizon of a black hole, which is a bizarre prediction that we've never tested, of course, yet.
Maybe someday. The next question is from an email. Why is plate tectonics believed to be important in the development of intelligent life?
It's not clear if it's necessary for intelligent life to form. It's a hypothesis that's out there. The argument basically goes that if you have a geologically dead planet, there's not enough geochemical dynamism to create the complex chemistry and eventually biochemistry that defines life. That's the simplest way to put it. So, on the converse, if you do have a dynamic planet with plate tectonics and a lot of energy flow through the mantle and into the crust and through the oceans, then that energy flow and that free energy that's available in that dynamic situation where material is churning, whether it's magma or water or compressed water inside rock, that sort of facilitates complex molecules forming because it increases the interactions. So that's a simple argument that plate tectonics is relevant to biology. It's not clear, however, you can't take that general argument and make it a prediction that you need plate tectonics to have intelligent life. We don't know enough about the evolution of life in general to make that statement.
Crawley Enterprises would like to know, does the many worlds interpretation of quantum mechanics have any relevance for astronomy?
Well, many worlds, invented as a theory by the physicist Hugh Everett in the 1950s, is a way of going beyond the Copenhagen interpretation of quantum mechanics by actually saying that rather than dealing with inherently uncertain probabilistic behavior, you actually have a situation where every probability of a different event actually happens, and so you have a endlessly bifurcating set of timelines where one actual probability becomes a probability of one and actually happens, and then somewhere else in a parallel train another probability becomes the actual case. And so these are the many world ideas of Hugh Everett. And it has a version that applies to cosmology, where you can have parallel universes and multiple universes with different outcomes. That's a rather different framing of many worlds, and I don't think it has a quantum mechanical interpretation. It's more conceptual interpretation.
The next question is, could dark matter be a type of substance leaking in from another universe?
There is an argument that dark matter represents matter, if you like, leaking in from a higher dimension. If we take some of the higher dimensional theories of cosmology that involve string theory, brain theory as it's called, then it's possible that you can have a force in a higher dimension that manifests in a subspace like our dimension, and that could be the force apparently of gravity that explains dark matter. So it is a possible idea of how to explain dark matter, but I wouldn't say it's the most likely interpretation. At the moment, the most likely interpretation is that dark matter is a new fundamental subatomic particle that has gravity but interacts very weakly with radiation.
The next question is from Pramod Argade, who asks, there is a total solar eclipse on April 8th, 2024, visible from a large part of the US. And other than watching it with appropriate glasses, can you talk about what interesting observations a common person could do to get the most from observing it?
Well, if you have a small telescope or even binoculars and you're using safe indirect viewing, never staring at the sun, you can set up a situation where in the eclipse you can make an image. You can just project an image. You don't have to put your eye there. You can project it onto a white piece of card on the ground, and you can actually see the corona. Well, that's a very nice observation to make, and you can really only see the corona during a solar eclipse. So that's probably the easiest thing that doesn't need any very special equipment. There's also a possibility of seeing flares and prominences, but for that you actually need a telescope. Again, not looking through it, but projecting the image onto a surface. But the magnified image would allow you to see flares and prominences coming off the surface.
Lee Bergen would like to know, what is the method and a general reference point, what is the method and a reference point for measuring the height of mountains on the moon, Mars, and dry planets in general?
Well, so mapping instruments on satellites have dualtimetry, and so they can measure, it's essentially laser ranging. So they can measure altimetry, and they can map out in a way that GPS would in 3 dimensions the shape or the surface of a planet. Referencing the altitude, though, of a point rather than mapping it out relatively in 3 dimensions involves understanding the gravity of the planet, because you've actually got to project where the center of the planet is. So the height of a mountain is obviously referenced to the center of the planet, and so you need gravity mapping as well as altimetry to make that calculation.
And then also, don't they create like a geoid, like a general shape of a planet that serves as a reference plane? I mean, how's that is an interesting question about how do they measure height? Is it from the lowest point? Is it from an average point?
I think it's an average point, but planets are not completely uniform and they're not completely symmetric. For instance, planets are rotating like the Earth, so they're oblate, so they're not perfect spheres anyway. So you have to take into account the rotation and the fact that they're oblate spheroids, and then you have to take into account the variation in density of the material through the planet to get the centroid of where the planet's gravity acts from. So it's non-trivial. You actually have to make a pretty good 3-dimensional model of a planet to do the altimetry the way that the question asked.
It's very interesting. The next question is from Larry Doucette, who would like to know, what do you see as the impact of the solar cycle peak in 2025 on the increasing number of satellites in low Earth orbit?
It's not clear what the next solar peak will be. We've had a very quiet sun phase the last few cycles. It seems to be rebounding, however, and so the next cycle the peak may be normal or more traditionally what we see over the last century. And in that case, the increased solar activity will have its various effects on telecommunication. Satellites, the telecommunication satellites are sort of built to be somewhat resistant to solar radiation because they have to be. They can't be destroyed by cosmic rays or solar radiation. So when a solar maximum occurs, it doesn't increase the radiation by a sufficient level to destroy or take out satellites. Solar flares could, however, but not just the general solar cycle itself. So it's unlikely that it'll have any devastating effect on the satellite population.
Eden would like to know if you could please explain sidereal time.
Sidereal time is from the Latin, is time by the stars. So you can keep time, you can keep civic time or terrestrial time, which is time by the Earth. And so time by the Earth would involve looking at the time between when the sun passes the meridian or its highest point in the sky one day and then the following day. That's a solar day. A sidereal day, however, is slightly different because a sidereal day is the time it takes a star to transit or to pass through the meridian and then to pass through the meridian the next day. And that's 4 minutes different from a solar day because in that day the Earth moves a little in its orbit of the sun. And so the vector from the Earth to the sun is pivoting as the Earth goes around the sun, whereas the vector towards a distant star is not changing from day to day. So astronomers keep sidereal time because it's sort of independent of the Earth's orbit.
The next question is from Dude, who asks, this might be a basic question, but how can scientists make sure that the probes they send or sent are 100% completely microbe-free to prevent contaminating other astronomical bodies?
It's an interesting question. It's an important question because NASA, as an organization, and the European Space Agency too, have tried to make a policy of sterilizing their spacecraft and not doing any contamination of the objects that they visit, especially if they land on an object. So basically the way that it's done is the satellite is built in a clean facility, and when it's finally installed, it's installed in a sealed facility or in a sealed cowling or a container that will sit on top of the rocket to get launched into orbit. So it's essentially sterilized in a clean room before it's installed in the container, which will then be put on the rocket. Then the rocket goes into orbit, and so in principle the spacecraft, as it reaches orbit or wherever its destination is, will have been sterilized. That's a fairly reliable procedure. Now microbes could potentially cling to the outside of the rocket because the rocket itself is not sterilized, and it is true that microbes have been found in the space station that must have got there aboard the rockets and the shuttles that visited the space station. So that sterilization is not perfect.
Our next question is from a live participant. Azaria Navarro asks, the core of Mars stopped moving a long time ago. Could this happen on Earth as well?
Right. The core of Mars has stopped moving. It does not have a dynamic core. It does not have a liquid core, and is not really geologically active and retains almost no magnetic field. So Mars has a very weak magnetic field and hence is irradiated by solar radiation. That cannot happen to the Earth because the mass of the Earth is so much larger. So the mass of the Earth is sufficient, and the radioactive heating within the metallic material of the core provides a lot of energy, and so that keeps the interior, it keeps a liquid layer in the core, and that means the Earth is unlikely to ever cool enough that its core solidifies.
The next question is from Ayush, who asks, since light and events observed with a telescope are from the past, then how are we sure that on a planet that we're observing that might have a similar environment to Earth, that there have not been any life forms that have developed?
Right. When we look out in space, we're looking back in time. However, for any objects where we might see life forms, those are essentially the exoplanets that have been discovered in the last few decades, and they're almost all within 3,000 or 5,000 light years. So they're in a nearby part of the galaxy. And that means we're only seeing them as they were a few millennia ago. And that's not very long in a geological time scale. So we're not looking so far back into the past. We're not finding life, for instance, or looking for life on very distant galaxies. And so we're not looking in practice far enough in the past that light travel time makes much difference.
Yang Pachankis would like to know, is it possible that our universe does not have the conditions for grand unification physics? And if so, what would that mean for astronomy and astrophysics?
It's not entirely clear what the backdrop for unification physics is, because we don't have a physical theory of grand unification. There are various ideas, and they've been explored in modest ways, I would say. It's not clear what the underlying physics of our universe is and what the initial conditions, if you like, were for the Big Bang, for example, which would constrain what the physics of our universe is. And so, yes, it's not clear how we would know whether we're on the right track for a grand unified theory, because we don't know what the sort of boundary conditions and the underlying basis for physical theory is emerging from the Big Bang.
We have an email question, which is, can you talk about who came up with the concept of a light year and when and why that was developed?
It's a good question. I don't think I know the historical origination of the term light year. I mean, it's a very basic astronomical unit. So I'm going to guess it emerged, in the Renaissance, or actually probably more recently, like in William Herschel's time when we started mapping out the galaxy. So you had to really know the distance to stars. I can sort of infer that it must have happened in the 19th century, because we didn't measure the distance to any star until Bessel did it in 1838. And so you don't even have light year distances that you're looking at until the middle of the 19th century.
And we'd also have to measure the speed of light too, I suppose. Wingman would like to know, we sometimes hear astronomers say that the universe's expansion is faster than the speed of light, or faster than light speed. How is this possible if light speed is supposed to be the cosmic speed limit?
So it is the case in the standard Big Bang model that the universe was expanding faster than light speed in the first roughly third of its history, first 3-4 billion years. That doesn't violate any law of physics, because the limit on the expansion rate of the universe in cosmology is defined by general relativity, not special relativity. Special relativity is the theory that sets a light speed limit for signal transfer, communication transfer, but it refers to a more static situation where you can synchronize clocks and exchange messages, and everyone knows they're on the same page or using the same clock. In the universe, there's no such constraint, because it's space-time itself that's expanding. And so there's no limit in the theory, general relativity, for how fast space-time can expand. And in the model of the Big Bang, based on tethered to data, it does show that the universe, all points in space-time, were moving away from each other faster than light speed for several billion years.
The next question is from Jan V, who asks, is there any time in the near future when we might be able to witness a supernova?
Well, we think so. Definitely, we're due. The last supernova in our galaxy was 1604, Kepler supernova, and the one before that, I think, 1572. So there have been a couple that are over 400 years ago. The average incidence rate should be roughly one a century, so we're definitely overdue. It makes it a good statistical bet that in our lifetimes there will be a supernova going off in our galaxy. But it could be anywhere in our galaxy. It could even be on the far side of a galaxy across from the galactic center, where obscuration and dust would even stop us seeing it. But if it was on our side of the galaxy within 100 light years, it would be a very impressive event and potentially a dying star visible in the daytime sky.
The next question is from Joel Sanchez. Do black holes have any sort of internal structure?
It's not clear if black holes have internal structure. The simple black hole theory just describes an event horizon, the region, the information membrane within which information is trapped by gravity. And then there's a singularity, a cusp of infinite density at the center, which is a troublesome physical concept, since physics does not accommodate singularities and infinite quantities. And that's really it. So there's no internal structure other than that predicted by general relativity. In the case of a spinning black hole, it's possible the singularity turns into a one-dimensional ring. That would be some level of structure, but otherwise it's not known what the internal structure of a black hole is. It's not known by observation, definitely, and even theory doesn't really say very much.
The next question is from Michael Serrera. Aside from finding life, what do you expect? I guess it's more like, what do you hypothesize, or what are some possibilities of what the next big discovery in astronomy could be?
It's always hard to predict. I mean, the nature of discoveries and the nature of astronomy is to surprise us. So yes, discovering life on exoplanets, which is an anticipated event. That wouldn't be a complete surprise at all, given what we know. That is probably the next really big thing. Other surprising discoveries might be discoveries about the Big Bang itself, about whether the Big Bang was one of many events, so perhaps some evidence of the multiverse theory. That would be an amazing discovery, which might come in through gravitational wave research, actually. Otherwise, it's really just hard to predict. It's one of the fun and exciting parts of astronomy, that it is so hard to predict the future.
Faisal is on with us live and asks a two-part question. I'll divide it into two sections. The first part is, what is the difference between a CCD camera and an infrared camera? So I should assume she means what's the difference between a traditional color,
Right.
Visible light camera and an infrared camera?
So a visible camera is basically a charge-coupled device, and that is typically a silicon substrate. And it's divided into individual wells or pixels where light interacts with the semiconductor, and so you're interacting, collecting photons and turning them into electrons, and the electrons build into these wells held by an electric charge that's applied, and then they're read out, and you count the electrons, and that tells you the signal that you convert back into light intensity. An infrared detector, well, thermal infrared detectors work quite differently, because detectors at infrared wavelengths beyond a few microns are essentially thermometers. They're really measuring heat rather than electromagnetic radiation itself. There are near-infrared wavelengths that operate more similarly to an optical CCD, but they use a different detector, a different substrate, not pure silicon, but something like indium antimonide or mercad telluride or other compounds, semiconductors.
The next question is sort of related to this. With these different techniques, is it possible to take photos of asteroids near Earth during the day and stars during the day using different wavelengths?
So in principle, you can't do optical astronomy in daylight, because the sun's light totally swamps any object. Witness the fact that you can never see an astronomical object in the sky during the day, except planets. You can't see stars. In the infrared, it's a little different, because infrared radiation is heat energy, basically. And so you can, in principle, but only very strong infrared signals can actually be seen in daytime. But it is possible to see certainly planets and occasionally stars, a few stars, during the daytime in infrared wavelengths.
David Wismer asks, since time stops at the event horizon of black holes, how can they actually finish merging so that we can detect them via LIGO?
That's a good question. That's in the reference frame of the black hole, time stops. So something that's falling into the black hole, its clock will freeze. However, the black hole itself as a physical object is governed by the laws of gravity, general relativity, but also it's a quasi-Newtonian situation. And so when black holes are orbiting each other, you can calculate in general relativity how they will orbit, and then they lose a little energy in the interaction, and then they merge together. So that is certainly possible, just because they are physical objects with mass moving through space.
The next question is, what is the general opinion on the nature of the asteroid Oumuamua among the astronomical community, and how plausible is Professor Loeb's suggestion of an artificial origin based on our current knowledge?
That's a difficult controversy, and I don't really want to wade into it because I'm not an expert on this subject. Avi Loeb, of course, is a cosmologist, so he's not an expert on planetary objects either, but he's learned a lot, and he's put out the hypothesis that Oumuamua, this highly elongated object that made a strange passing trajectory through the solar system and then left, was an interloper that was a physical artifact from an alien civilization. And his argument was just that its orbit and its physical properties, its great elongation, was such that it didn't seem like any solar system body anyone had seen before. It is unusual, for sure, and its orbit is unusual. But the planetary science community has continued to work on it, and the evidence or the papers from the last year or so pretty strongly suggest they have hypotheses for how it can just be a normal but unusual solar system object and not an alien visitation. So the weight of evidence puts Loeb in a small minority in holding out that it's an alien artifact.
The next question is from Mark Harding. Is there a limitation on how near to the moment of the Big Bang that we would be able to view events?
There is a rough limit. The traditional limit of viewing towards the Big Bang is the microwave background radiation. So looking at those longer wavelengths of millimeters, you're looking at radiation that's roughly 400,000 years after the Big Bang. It's a baby picture of the universe. There's more indirect evidence of the universe at earlier states, but it's not in the form of an image. That 400,000 years is the oldest we can see a picture of the universe. Before that, we have indirect evidence based on the amount of helium in the universe and how it was produced when the universe itself was very hot. We have evidence based on fundamental particles and unification theories of physics of what might have been happening at fractions of a second after the Big Bang, but at that point we're getting speculative.
The next question is from Hassanyan, who asks, how important are exoplanets for understanding life in the universe? Or more generally, how can exoplanets be used for understanding life in our universe?
Well, the exoplanet population, now numbering over 5,300, is extremely important for deciding whether biology was a unique accident on the Earth or whether it's part of a general phenomenon. And so at the moment we can't answer that question. We have not inspected any exoplanet in enough detail and carefully enough to decide whether it's a living world or not. It's a very challenging set of observations, but there are observations that are about to be possible. So it's a very exciting time. So I think exoplanet research will answer the question of, is there life, microbial life, typically elsewhere? And I think it'll do so within 5 to 7 years.
David Wismer would like to know, imagine an Earth clone as it existed in 1 AD. How close would we have to be to it to prove life existed, and what markers would you detect? So I think what they're asking is, how would we detect life, perhaps intelligent life, on a planet, and how close would we have to be to see something like Earth as it existed in 1 AD?
We would have to be very close to an exoplanet to see any detail on it. The exoplanets that have been cataloged, thousands of them, are most of them don't even have images. They're just indirect measurements of a transit, eclipse, and Doppler wobble by Doppler effect. So indirect methods. To see exoplanet, you'd have to be closer than the closest star distance, because Proxima Centauri is the nearest star, just under 4 light years away, and it very likely has terrestrial planets, but we can't make images of those. So we're quite hampered in direct scrutiny of exoplanets right now, just by the fact that the star they orbit, even when it's a red dwarf, so a dim star, is hundreds of millions and maybe even billions of times brighter than the planet.
Are there any other biomarkers that one could sense? So like, are there characteristic like fingerprints that we could look for in the atmospheres of star? I mean, do humans do something to the planet that could be detectable?
So microbes do something, which is what happened on the Earth. So they put oxygen in our air at 1 part in 5 roughly, and that's what we would look for on exoplanets. We look for a photosynthetic process or oxygen production that gave us the air we breathe, because that's a good sign of life. Methane is another biomarker. Water is a biomarker too, because we think life needs water to exist. So a completely bone-dry planet probably doesn't have life. And there are other markers in the atmosphere that are called technosignatures, because they don't just indicate microbes, they actually point to technology or civilization or advanced creatures. And the classic one might be nitrous oxide. So nitrous oxide is geologically quite rare, but is an industrial effluent. So if you see an early technology, because industrial society is now over, we're using computers and hopefully we won't need fossil fuels much longer. But if you see an intelligent civilization that's sort of running on dirty energy, then those industrial pollutants, and there's others, will be visible in the atmosphere, and that may be a good indirect way of detecting intelligent civilizations.
So it's 11 o'clock. We'll do one final question, and then we'll wrap up for today. Mr. P asks, are any remote sensing astrobiology projects planned for Venus in the near future?
Yes, NASA approved or green-lighted the development study, Phase B, I think they call it, of a Venus mapper, Venus orbiter and lander, which will, I'm not sure quite when it's going to deliver. NASA's timelines for these missions are a little uncertain because their budget is uncertain, but it has green-lighted Venus, an exciting Venus mission, because for the first time in decades, since Soviet experiments in the 60s, I think, we're going to land something on the surface of Venus and measure the atmosphere as we descend to the surface. Unlike the Venera probes of the Russians, most of which died without taking any data, and I think one of which took minutes worth of data before it melted and died, this probe is designed to survive for weeks on the surface. It won't survive longer than that, but it'll survive for weeks taking data, which is quite extraordinary given the physical conditions. So that's an exciting mission. I think it's due to, we might see results from that early in the next decade. Good questions, as always, on all subjects, and it's good to be with you. I think we have one more session scheduled, but we'll defer to Matthew on when that is, and otherwise, I'll thanks him for his facilitation, and we'll be with you in the future.
Excellent. I'm happy to help out. That's it's going to be May 22nd. It's another Monday session, and that will be on Twitch. So if you're on our email lists from our courses, I've already put that on the latest emails, but if not, then look for us on Twitch on the 22nd. So thank you all for being here. We appreciate your time, and we look forward to seeing you again in about 2 weeks. Take care, everyone.
Okay.